So yes, I'm here to advertise another program that is called EPIq, and this is, can be seen as a post-processing package that is useful to interpolate thanks to the Wannier transformation. And I don't know if you are really familiar to this, so maybe I can take some time to explain you better what I'm talking about. So as you have seen, what? Zoom in, okay. I can do that. Is this better?
Yeah.
Okay. Good. So, okay, this is a bit of a banner. Just to advertise the site and the paper that we just submitted. So, what is interpolation? I think you know this. Maybe the thing that you it's better that I remind you is why is this important and what is Wannier interpolation. So, indeed, we need interpolation because we are studying the properties of a material that, thanks to the block theorem, are usually defined upon a certain grid, the K-mesh usually, and this that is sampling the first period zone. And this mesh is, let's say, the only way to treat an infinite system in a discrete way. And usually, since you have to study the properties of a sample, you have to study averages of quantities defined on this K-space. And of course, if you are studying averages, the number and the goodness of the fit of the sampling that you are doing depends on the function that you are integrating. And so this is really a sketchy way to describe the need, to show the need of a good sampling whenever you have to sample a function that is localized. So that is a really discontinuous behavior. On the left column, you see that if I have a really localized function, if I try to represent it with a finite number of sampling of points, it will completely miss the behavior of such a function. Instead, I need really a finer mesh in order to capture the behavior. This is the case in most. This is the case in material science because whenever we are talking about metals, because as you know, the Fermi-Dirac is the function describing the occupation of the electronic system in a metal, in a solid. And when you are working with metals, you are not interested in the, let's say, far constant behavior of this function, but indeed you are interested on the edge of this function that is called the, let's say, the Fermi surface of your barrier and so on. So you are looking indeed into the study of a discontinuous function. So discontinuous and like the EV side, or just like the delta Dirac, that is the derivative of the EV side function. So indeed, when you are trying to describe metals with a finite mesh, you need to be really accurate in the way you are sampling your beer and so on. And this is the reason why you need a really efficient way to capture and to describe your sampling and your quantities over a finite sampling. And the idea is that we will use not the usual Fourier transformation, let's say, but because that is not possible, because in the properties that we are looking for interpolate are defined as a matrix element, a sandwich between two block function, and this block function has what is called an arbitrariness, so they are defined up to an arbitrary phase in front of each block function. So there is this arbitrariness in doing a Fourier transformation in the real space. This arbitrariness gives you the opportunity to perform good or bad Fourier interpolation, let's say. So indeed, the Wannier interpolation, the Wannier stands for a way to obtain an optimally localized representation in real space. And if you get an optimally localized representation in real space, you will have a really smooth representation in the K space. So it is the best way to perform a Fourier interpolation of quantities defined upon a block function basis. How much of you have already been lost in this? Okay, maybe I should, because the problem is that I have to do this introduction without having a slide, so maybe I should have put more schematic figure, I don't know. So the basic idea of Wannier interpolation is that we start from a computation with a very few K points, and it is performed with your preferred ab initio software. And then you transform these quantities in real space thanks to this optimally transformation that is called Wannier transformation. And then you transform back these properties on a denser, much denser grid on the K space, on the Q space. And you obtain a property that is really represent a different sample with a very high definition, let's say, to continue this rhetoric figure speech. So this is a schematic picture of what I was saying to you, and indeed this is also the way, the path that you have to follow if you want to perform your calculation from scratch. So as we have done in the hands-on session beforehand, we start with a PW calculation that is giving us the block function. And then we should perform a DFPT calculation to obtain the properties we want on a not refined K mesh, K grid. And afterwards, whenever we have the properties of interest, that in this case are electron-phonon matrix elements, we can exploit the optimally Fourier transformation obtained thanks to what is called a Wannierization of the system, so an optimal representation in real space, optimally localized in real space. And after you have all this preliminary file, you can start doing your interpolation. And so that is the part when EPIq comes in, and he take the electron-phonon matrix element you have performed on the rough grid, and thanks to the matrix that represents your transformation real space, it can interpolate the properties you need and then compute the response function and the properties that you are looking for. So let's say the lower panel, similar to the one that has been done in the before hands-on session. The upper one is regarding the Wannierization. I will not talk about this. And we just will take the the result of this preliminary calculation, and we'll use EPIq to perform the calculation of the line width just as before, but power up with the speed up of the Wannier interpolation. Okay. So what we will be starting with, if you go to the directory present in the here, okay, the zipped folder that has been given to you with the latest email, you will see the folder, the 8 hands-on section, the EPIq one, and you will find these three, these three directory. This one, EPIq one, is the one where I installed the software. So I don't know where you have downloaded and installed EPIq. And the other two, math element and dynamical matrices, are the directory containing the preliminary file that has been computed for you, as well as the Wannierization file that are here, and they are this .chk and So I don't know if you have encountered any problem during the installation of EPIq. If so, I don't know, raise your hand. Somebody will go and support you. Is that a... What is the problem? Yeah, this one, I don't know what is it, but I think it is. Okay, so this is the okay. Okay, so I can delete this, let's say. Move to trash, good. And so you are fine now? Okay, and do you have the software installed? Okay, good. That was something that I feel. So, how can I enter? Okay. Okay. For example, the matrix element looks like this. You don't have to open them, but they are just preliminary files, so don't be scary about their numbers. The computer will handle them for you. And instead, in the dynamical matrix directory, you can find two sets of dynamical matrices, just like the ones that you encountered before. These are produced by Quantum Espresso, so they have the same layout. When you have all this, the information about the basis cell, and these are indeed the dynamical matrix in the displacement Cartesian basis set. And there are two sets of dynamical matrices because one are the ones computed without the anharmonicity provided by SHA, and the other one, the one that are called with the SSCHA label, are the one that were computed for you by the SHA engineering. So we will see later on in the exercise what will be the difference of using anharmonic, of considering anharmonic effect in the line width calculation. But indeed, this hands-on session was thought to be more regarding how to feel comfortable with this software. So we will not perform a really high quality computation, let's say. We will just select an easy computation that runs fast on your computer so that you can not be overfed by information, and you can keep it easy. Okay, so where is this? I did open the, okay, this one, I think. Okay, perfect. So you should be in this situation where in the EPIq folder. Yeah.
Can I make a question? So,
of course.
The electron-fonon matrix elements, how did you calculate them with?
Yeah, without your power up, so they are just harmonic matrix elements.
Yeah, but this is just in Quantum Espresso.
Yes.
There is a flag to print those or something like that, or.
Yeah, there is a flag that was. Well, maybe I can take the chance to tell you about the story of this project. Indeed, it's a quite old software that just now was pulled over from a closed drawer from the head of the project. So indeed, there is in Quantum Espresso a really old label or tag that was put years ago by Matteo Calandra that allows to print out the matrix element. Okay. But nobody knows about it because he kept this a bit hidden. And now that we release the project, I hope that it will be more advertised as a label. Okay. And yes, I think the label is elfmat_Wannier. And he performed just the bracket of the deformation potential. Sorry. The bracket of the deformation potential with the block, computed in the harmonic way of Quantum Espresso, between the block function and printed out in a really dummy way. So I think it is not completely parallelized.
Okay, good.
Okay. So you should be in this situation when your hands-on directory in this the directory you choose. It appears the EPIq directory with the program and the executable, and you can, let's say, you can see both the Wannierization files and the matrices element and the dynamical matrices directory. And so we are ready to start. And yes, and amongst the possible calculations that are already implemented in EPIq, there are a few. We choose the electron-phonon line width, the electron-phonon contribution to the phonon line width, both for the audience and because it's quite straightforward to run this computation. And then we give a bit more aesthetic result. We can computing the anisotropic Mitter-Ashberg, and the latest plot, if we manage to arrive to reach that point, would be a beautiful graph resolved over the key point of the MOS dual system. So indeed, in EPIq, you can also compute adiabatic and non-adiabatic force constants that exploit an interesting framework that is a differential variational framework that allows you to, let's say, it's an approximated framework that allows you to control the error. So a really fast and accurate way to compute non-adiabatic force constants. And also isotropic and isotropic Mitter-Ashberg equation is included in the package. And you can also perform double resonance Raman scattering, yes, calculation, and also the electron lifetime realization time. So indeed, the properties that you can compute afterwards your interpolation routine regards both electron and phonon properties of the system. And so we thought that it would be a great idea to divide our input file in this three name list. Let's say a general control name list, one that it accounts for the properties of the electrons, and the other one for the phonons. And this program, the EPIq package, is a bit old-fashioned. So it's completely written in Fortran FF90. I don't know if you will like it or not, because it has some pros and cons. For example, it's more stable amongst the years, but it's a bit more cumbersome to be read. And so let's say that the input file will look alike from the one. They are quite similar to the one that are used in Quantum Espresso. So maybe someone will find them familiar. I don't know. So what we should do? The first thing that we have to do is to transform our properties of interest, so the electron-phonon matrix element, in the optimal real space representation. In order, what? It was me? Okay. Oh, sorry. And in order to do this, we can just copy and paste this input file, but it's quite straightforward. There are really few labels, so it's quite straightforward to understand what it's doing. He asking the program to dump the G, so the deformation potential matrix element, over the real space, and we have to give him a prefix, just a name for the system that we are interested to simulate, and we should point it out to the program where the matrix element file are stored. And since we are just interested in the matrix element, we don't have to give any information about the electrons, and instead we have to inform, let's say, the program on what was the grid that was used to compute the matrix element. So this 881 is something that you have to put because we choose to use this grid for the DFT calculation. The system that we are going to compute and calculate the line width is the MOS S2, that is a dope monolayer that is really close to a charge density wave transition. So we already know that an harmonic effect will be present. And since it's a 2D material, and that's explaining why we have to put the third index to 1, because there is no need for any Q-points in the Z direction if we are studying a 2D material. And so we can just copy and paste and see what happens. Okay. I don't know what you are doing right now, but if you had already ahead or you are far behind, just let me know, because it's useless if I just here talking by myself. So please give me feedback and tell me what are you doing. So, okay, anyway, let's see where I am, okay. EPIq, okay, now this is the folder where I installed the software. Okay, here I am the main folder, and I can starting to write my input file that I can call dump.in. And let's see if I can copy and paste, because it's quite difficult. No, okay, perfect. Let's try again.
Button in the mouse works.
Ah, okay, that's a good hint. Let's try that. Ale, that is, okay, thank you. Okay. So this, I can close it now, and I can run it. So let's say EPIq folder. Let's look for the binary file. If everything compiled well, if only ever. Yeah, maybe that is. Let's offer it. Binary, okay. Let's take a look. Okay, we have the main binary file that is epic.x, and that is taking into account to interpolate, so it's the main drive of the package. And then you can see a family of post-processing tools that we will be using, but just keep it to the main interpolation routine. So that's minus. Okay. I call it dump.in. Let's redirect the output to the dump.out file. Let's see if it throws back some error. Let's hope not. Okay. Minus S out. Perfect. It's not really. It's just ventilating hot. Wonderful. Okay, maybe the redirection was a problem for him. Okay, this is the wrong way to do it, because we are not using the parallelization power. If we indeed exploit, I don't know, how many processors I have in this? 4? Wow. Let's use them all. I don't know if you are accustomed to MP run, but you just have to run the program with this flag and then explicitly define the number of processors you will be using. And then we have to wait to the program to compute the transformation in real space and save it.
Marcus, you hear that?
Fortunately, this operation will be has to be done just once, because once you are in the optimal real space, you can perform back the Wannier interpolation. How many times do you like?
Here, the name of the matrix elements, it's by default this one, right? So
yeah,
once you keep it has to be this name, right?
Yes, yes.
Okay.
Indeed, the project is old, but the program is quite new, so we are looking for your feedback. If you find something that is better from a user point of view, we can implement it in no time. Okay?
Sorry, just a question. So now we have transformed in real space the matrix element given by quantum express.
Yes, that's it.
Okay.
The matrix element and also the Hamiltonian. And you can find it here in this bin file.
Okay.
It's not really user-friendly because it's a binary format, but it's really compact, so it uses quite few spaces than the ASCII format.
So up to now, no Wannier interpolation yet.
We are halfway of the Wannier interpolation. We are in the optimal representation in real space. And indeed, we should check that. If you follow the tutorial, the first thing to do after you dump the real space representation is to look for these files that are the output files of there are two test files of the damping where the matrix elements are plotted and saved against the real space displacement, these are. So you can see, and we should do right now, the test of seeing the localization in real space of the matrix element and of the Hamiltonian. So yeah, indeed, we transform now in the real space, and we have to check that it's localized, because if it's not, then the interpolation would be a terrible one. So the first thing to do is to well, go to the output file and check it out that this this one, for example, that this dumped the localization of real space went as we hoped it would. So it's maximally localized. So let's see. I don't know which program do you prefer, Newplot or Python Matplotlib. I think that I will go with Matplotlib. I will try to write down as I think you are doing right now, so we are at the same speed, but maybe I'm lower than you. So if you get bored, just tell me, because I have the solution. So if I have to skip something, I can. Why I don't like it? Because it's a bit. So let's import NumPy and Matplotlib.
You have an extra U in NumPy.
Well, I'm quite a taper. Did you understand why it's important need to be localized in real space? Or there is an
The importer of Matplotlib.
You want
Yeah, of
first
course.
comment?
Thank you. Yeah, I know.
Spanish keyboard.
Yeah. Oh. What is that? Okay. Seems like we are quite okay. Parentheses are in the right place. What was called the file? Let's look at it. Okay. Let's take the first. Let's see if. Okay. Perfect.
What is here? Why do you have different files?
What?
What is the mu one, mu two, mu three? So
Yes, this is this file is named with the prefix you choose, and then GW is just telling you that is the element matrix element, of the electron-phonon. R is labeling the fact that it's in real space. And then mu1 it stands for the first mode of your displacement in the, so it indicates the modes of your phonon, let's say, in the harmonic description.
Just a small comment. Actually, at this point, since you are still in the basically you're putting in real space the matrix element that you got from Espresso. In that routine that Guillermo was mentioning before, actually what you do is you calculate the matrix element in a Cartesian basis. So actually mu1 up to mu9 here represent the 9 Cartesian coordinates of the atoms in the MOS2 unit cell.
I see. So the localization of this Wannier transformation of the electron-phonon, the centers are the atom positions. No. So there is a physical meaning in the centers.
Yeah, more or less. It depends because the Wannier.
Okay, yeah.
It's not sure that they're localized.
Okay. So it's just the regular Wannier.
Yeah. Wannierization.
So let's see. I got that right. I did not.
And this localization, you don't need start guess for the.
You do, but it's not presented in the tutorial. Like here, you already have the final result of the Wannierization, which is encoded in that SSCHA file.
Yeah.
But actually, yes, you have to perform the Wannierization. In a regular.
Indeed, in the latest version of the Wannier 90 code, there is an automatic wave to perform the optimal choice of the starting orbitals.
Really?
So, yeah.
Oh, this is good news. Right?
Yeah, I don't remember the keyword.
I haven't been lucky using it. Maybe I'm not very good at
Yeah. Well, the physical insight is always better, you know, if you got an help. So, if we did a good job in performing the Wannier transformation for you, you will find that this let's say this shape that is quite ugly because I don't really care about the aesthetics of the graph, but the most important fact is that with the growing distance from the centroid, the matrix element is rapidly decaying, so it means that it's localized in space. So indeed, if we hadn't done a good Wannier transformation, we would find here a lot of other spurious, almost a constant function.
May I ask a question here?
Yep.
So this also depends on the qubit you have, right? So if you have done like a smaller, instead of an 881, you have done a 331.
Yeah.
Maybe you are.
This is yes, because indeed, if I manage to get to the if you look to the matrix element as Jon was saying, you see that they depends on two momenta, K and Q. So indeed, two transformations are needed, one for decay and one for a Q point. And so indeed, you have to check both the real space localization over the K space and over the Q space. So this difference is labeled here like as moving like EL, that stands for electron. So it's the R, so the position of the electron in the electron subspace. Instead, here where is the pH as intuitively is regarding the phonon. So if I replace here, this one. Now I will be plotting and I will be checking. No, let's do this. I will be plotting we'll be checking the localization over the Q space. As you can see, maybe 1 point is a bit higher than expected, but we got up to the 14 unit cell, so indefinitely converge and is definitely localized. So we can proceed and come back to compute some physical properties. Okay, just follow. Let's come back to the F. Okay, so it can now the input file for EPIq is a bit more complex, but indeed it really it's really similar to the one before. I'll be adding a bit more information. Maybe I can copy it and then I will explain you what is label, what is the meaning of each label. So now, yep.
Sorry, I wasn't very clear to me what was the thing that was supposed to get out from that graph. The one that looked very messy.
Yeah, of course,
okay, so.
because I didn't put any labels, so maybe it's definitely my fault. Let's see. So maybe I have to replot it. So just give me a minute. Okay, but then let's try again. Okay, so this one.
Well, I guess both. There was
Okay.
one that looked quite similar also. It was also very
Yeah. Okay, this one on the x-axis, you have the distance from your center in supercell. So you know that when you switch from the K space to the real space, the number of your K points would be the number of the unit cell you are representing your supercell. So this is the number of, and so the distance from your center on the supercell, and these are the matrix element, let's say, components on that unit cell. So this means that this matrix element, that is the the first Cartesian displacement, is non-zero only up to the 4th unit cell, and then it became 0. So it's really localized in your supercell. So you can describe it completely without losing information. If I would have used less K points or less Q points, I wouldn't be able to reach this value. So I would just be stopping before. And so I would lose the tail of this function, and this representation wouldn't be enough to let's say describe completely the matrix element.
So if I understand correctly, that means that we could have used less less Q points, or we would have to need more Q points.
What?
So does it mean that because it sort of stopped at 4?
Yeah, it's not the most efficient one, you say.
Yeah.
Okay, yeah, that's true, but this is just a preliminary properties. What we will be seeing is that then we have to check the convergence on the properties we are interested to. So we will be computing the line width, and we will check that with different K point, the values remains a convergence. So indeed, seeing in other ways, yes, looking at this graph, I could thought to be using let's say too brute force, too much power. I'm not efficient, but indeed you should not look at that in this way, because this is just a preliminary properties. You have to look at the properties that you are interested to check the convergence and maybe try to be more efficient.
Thank you.
And there were two graphs, because one was the real space transformation for the K point, and the other one for the Q point, because we are describing a function that is defined over the K and Q grid, because we are looking at this let's open it again. The matrix element of the electron-phonon coupling here, as you can see, is defined upon both the momenta of electrons and the displacement.
So just to add on what Guillermo is telling you, essentially this is a preliminary test, and the aim of this test is just to check that the Fourier transform to the real space that you perform is localized. So if you see that at the end of that graph the function is going to 0, you are okay. But this doesn't tell you much about the efficiency of the localization process, because this is not the only operator that you're localizing. So essentially that depends on your Wannierization. And what I would say is that it's not really straightforward to be sure that, for example, that there, if you reduce the points in the Wannierization, you will still get a localized function. It's not the linear, let's say. So you know that in this case it is localized. You don't know anything else. And also, adding up to this point, this is important to check because, as Guillermo was mentioning, we have a gauge freedom for the wave functions. So if you by mistake are using different wave functions to calculate the phonons and the Wannier properties, you would see that this graph here becomes all no decaying of the function, and you see that the function is just random in the real space. So this is a check just to be sure that you're consistent and everything is running smoothly. But you should just see if the function is decaying, and that's okay.
Fortunately, that is the case, so we can go forward and perform our first calculation. So in the control name list, we should explicitly specify the prefix again. And now, instead of dumping the G matrix element, we will be performing a pH, so a phonon line with calculation. And we will be reading the already dumped element, matrix element in the real space. And okay, then this is this flag out to JSON. That is a bit a prototype, because as I was saying, the project is old and it's all written in Fortran. We are looking for being a bit up to date, so we are trying to integrate it with Python. And I don't know if you already know the JSON format, but it's a hashy way that can be automatically parsed in Python. So you can read the code that is outputting, but also your Python library can read it for you. So it's quite easy to, let's say, to use the result of your calculation using Python. Then now we have to specify some quantities for the electrons, because if you look at the Allen formula that we are computing, we have to, like was done in the previous section, we have to compute these two delta functions that, of course, when you compute them numerically, you have to use let's say a smeared function that will sample your properties, just like a delta will do. But this function is, for example, a Gaussian that has a finite length. So the first parameter we have to explicitly define are the width of this Gaussian and the type of smearing function we will be using. So this mGauss, just like in Quantum Espresso, will define that the type of smearing function that will be Gaussian if we put it to 0. And then the sigma min and sigma max are telling the EPIq computation software to, let's say, compute the same quantities for different temperatures, because the width of the Gaussian, just like before, can be interpreted like a finite temperature affecting your Fermi-Dirac occupation.
One more question. This is in Rippers?
Yes, yes, just for traditional Quantum Espresso integration.
Okay.
And then now, for the first time, we have to also specify where the dynamical matrices are stored. And so if we will be computing quantities taking into account anharmonic effects or not. So we have to specify that we will use let's say a custom name for the matrix element, and that we have to specify which name is. That is the path where the matrix, the dynamical matrices are stored. And then yes, then we have to also specify which will be the K-grid upon which we are interpolating back to perform this calculation. So up to now, turning back to the first schematic figure, we have, for you, we have performed the few K-points calculation. Together, we transform it in the real space localized representation. And now we are going back to the K-space to perform the let's say, the high definition calculation. And so we have to specify the grid, the high definition grid of the K points where will be doing this calculation. And this is done here when writing 4 by 4 by 1 is just telling the calculation to be performed on a Monk-Korsk-Pak grid for a bidimensional system. And then we have to specify also the number of Q points where we will be doing this calculation. And so as a starting point, I choose the point M in the relevant zone. And that's it, I think. So we have just to run the code and see what will be the line width at the M point of the relevant zone. So, well, let's see if I paste it in the right way. Okay, what we have here, yes. Okay, we'll be looking for 5 different temperatures. Okay. Is it copied twice? I think it's copied twice. So indeed, something will. Okay, so I have to. Okay. So we take the EPIq binary file, we'll give him the input file, we'll try to redirect it to an output file of our choice, and let's see how the output file will look like using a Spanish keyboard. Okay, we indeed choose a really fast exercise for you because it already ended. Did it already ended on your laptop too? Yeah. Okay, that's good. Oh, somebody answered this time. It's going better. Okay. Good. Okay, so let's take a look to the output file. Okay, this is just some price show off for us, and also the indication for how to cite this work. And okay, well, let's see. It doesn't tell you very much. What it's telling you, for example, is that it performed indeed the computation over different temperatures, and for the minimal and maximal meaning that you choose, you also recompute the Fermi shift, the Fermi energy, because you know if you are considering an higher temperature, your Fermi surface will vary, will increase, for example, the Fermi energy, and so it will compute for you this different Fermi surface. And okay, and then he's telling me that he use the parallelization of a K point. That's good because you know we have both K and Q points, and they are both independent, so we can choose to be parallelized over the K on the Q space, but the program will take care by himself and choose the better option for you. And then it's telling me that he print out the output file, okay, and we can, where the data are stored. So we can look at the output file. Let's see, okay, so, okay, this one, for example. Okay, that's why I introduced the JSON format, because this is a bit, scaring. As it's really a wall of text output file. But you can see that indeed we are looking to the key point M of the view and so on, and that we are studying different mode, so different displacement. And for each displacement, he computed for us also the frequency of that mode. And for the different temperature that I can see here in electron volt, just for being a bit more confusing with units. And then I have these columns where each of that is indeed representing one. Some of them are different approximation of the lambda of the lifetime, and some of them are, for example, the double delta that is is quantifying the nesting function. In order to understand which is which, because I don't remember them by heart, I will look in this header of the output file, and we found out that the first column is the smearing, the other one is the line with computed with the Allen formula, and so on, so forth. But if this process doesn't like you, you can just open the JSON file. Maybe it's as ugly as the one before, but it's work differently. If you are accustomed to Python, this is a dict, and this is the label telling you what is the key point in the Cartesian and the fractional units. And for each key point, you have the same information as before. So, for example, the temperature to which the calculation was performed, the double delta that is accounting for the description of the nesting, the density of state, the Fermi energy, the new Fermi energy computed with the smearing. And then for each mode, you have the frequency of the mode and the different type of approximation that you are interested into looking at. So the first thing to do is always to check if the numbers we have got are trustable or not. So, for example, if we are at convergence or not. So the first thing to do would be studying the values of, for example, of a specific line width for a specific mode as a function of the smearing that we used, and we can do it plotting it. So I don't know if you like matplotlib or just as before. I can try to do it live. I don't know if you ever perform a convergence study, but the idea is that since we are looking for describe a localized function with a finite mesh, we can do two things. We can deform the function and make it less localized and using a poor grid, and that it would be still a result of convergence. Or we can, but maybe not the conversion that we are in, it's not the configuration we are interested into. Or maybe we can, let's say, make the right localized function with a denser mesh. So it's very easy to speak while typing. Okay. So I load the file again. This time I will be using the JSON file. Where are they? Okay. Okay, just opening the file. JSON.load is the function we are looking for. It will parse the ASCII file. So we have just to say the name of the file. The name of the file. This would be the cool. Okay. No. This one. Okay. Good. And the file is called. How is it called? mos._lambda.json. Here it is. Good. Okay. Wow. So let's try to. Okay, so as I was saying you before, no. This is a dict. This is not okay. This is a dict. So if I'm just interested in the first coup point, I will, for example, the M coup point. I can select it in this way. Then I can. I'm interested in plotting the in the x-axis the smearing. I have a problem with square brackets. And okay. No. Here it is. Okay. Sorry. Okay. So the temperature is called just T. So in this way, I will choose to put the temperature in the x-axis instead. I'm interested in the first mode, for example. So I will again put up 1 here. And then Allen. Gamma Allen. Okay, let's see if this is the right way to do it. W__. Come on. I don't like it. Okay, so what is this? This is the line width as a function of temperature for the coup points, the first coup point, as it said here, so the end point. And indeed, we are looking just at the first mode. And so indeed, this is just the first mode line width of the coup point. If I would like to plot the other mode, I just can do a loop. I don't remember how many modes there are. Let's see, I don't know, 9, I think.
Yes.
Okay. Join from the back of the audience. Someone is calling for you. Graph parentheses is a challenge. Okay. And it's, yeah, thank you. Okay. Let's see if this is working. Okay. Well, indeed, I prepare in the tutorial a fancier graph, so maybe I just can copy and paste it. Maybe it would have been better to do it just. But so you had the time to think about what we are doing, maybe come up with some interesting questions.
Does anyone have a question at this moment?
Good. That's the problem with Python. Also, this symbol, I don't think it's cool. Let's try if this script give you a better, more aesthetic graph. Of course not. That would be the problem. I'm trying a little. Okay, it just. Points. Okay. Wonderful. Wonderful plot. Okay. So these are all the modes, all the line width for all the modes. As you can see on the y-axis, you have the line width in MEV, and the x-axis, you have the temperature in electron volt. And so what we can do now is perform another computation, just like this one, but with a lot of a denser mesh that will allow us to check what are the points that are convergence for a certain temperature and which are not. First of all, I have to rename the file because if not, it would be overwritten. So we can say just harmonic and 4x4x4. Then I can rerun the script, just changing a bit the input file. And in your opinion, where should I put the new grid? This is quite a lame question, but I don't know. Maybe in this way it's more interactive. What should I change? What number, what input should I change in order to change the mesh over the k-space where I'm computing the line width?
Who knows the answer?
Yeah, that's it. Yeah, I know it's a lame question, but you know, you are the only one to answer. So, okay, good. Yeah, you are a bit more freedom. You can do whatever you want indeed. You can, as you were saying, you can define the Q points over a mesh if you are interested. That it could be the case when you perform, for example, a mesh, and then you use the mesh to be interpolated in a finer mesh or just in a line. And you can do that just changing this crystal variable and putting, for example, automatic. This would tell the software to create a mesh for you. Or indeed, you can also just input a file where you store the points you are interested into. So you just write this other label and then, I don't know, write the path to the file. I hope that they are the actual label, but since I'm not good with memories, I can always check on the website and on the documentation. So I have the chance also to show you the website. Let's see if it's working. Okay. Okay, we are connected to the internet. So this is the website that we have done, but we are not software engineering, so we did our best, and that's the result. And yes, we are not neither graphics. I don't know if you if you have the doubt. And okay, so we can look at the input documentation, and we can find out that these are all the labels that you can use. And I already okay. Maybe a bit lower.
So just to go on what we are most telling you, actually, as I know that you're interested in calculating sort of mapping properties, what you would like to do in that case is to perform the calculation using the automatic mesh. Then, of course, EPIq works in such a way that all the data is put in this file, this line file, and then with post-processing, you can calculate, for example, the lambda, or I don't know, the lambda over a path, or other properties of interest, depending on the problem you are interested in. However, the core functionality of EPIq is that you have this starting, dumping process to the real space, then you have this second process where you calculate something, which is in this case the line width, and then you have some post-processing that can be whatever, just to calculate the property that you're interested in. So of course, in that case, it's automatic.
Okay, so
internally the code, when you take advantage of the interpolation, you are using so you use it to interpolate energies or also to interpolate block states.
yeah.
So,
So,
I don't know if my question is clear.
yeah, so you are saying that we interpret also the wave function besides the eigenvalues of the Hamiltonian.
Yeah.
No, indeed, no. We just interpolate because we are studying just response function, and the response function depends on the, as you said, the eigenvalues and on the, let's say, the eigenvector, but on the matrix element. So interpolating both the eigenvector and the matrix element is just doing twice the same thing. So we prefer to interpolate the eigenvector and the matrix element instead of the eigenvector, but we can do both indeed.
So in a way, we are not interpolating the single function, but we're interpolating the whole matrix element. So indeed, inside this interpolation, there is the information about the interpolation of the wave function.
The way that the code is built is meant to be, let's say, a main drive for Wannier interpolation. So you can put whatever operator you have in mind, and also the identity. So in that case, you would be, for example, interpolating not the single wave function, but the overlap of two wave function.
Okay, the question I have is, so that's why you are concerned about the Wannier functions being actually localized. So it's not enough to reproduce the eigenvalues, the energy landscape. And have you tried with systems where there is an obstruction to the Wannierization?
So actually, we didn't try explicitly about that, but the point is that in that case, you're sure that you're not maximally localized strictly, but most of the time you can still get some kind of localized representation. So you are not really maximally localized, but I mean, then you have to check case to case. But in general, this localization problem is even bigger in the sense that now we are interpolating electron-phonon matrix elements, and those tend to be localized, but many operators are not.
Yeah.
So in general, it depends a lot on the operator, and of course, if you have a topological abstraction to the localization, you should be particularly careful about that. But for example, I was studying not with EPIq, but still with Wannier, some topological insulators, and even if you get like more delocalized Wannier function, you still can consider yourself localized. But then you have to check with that test that we showed you before.
And this is a question more related to practical maybe. So do you know an easy way, I mean the fastest way or the less painful way to check the actual localization of the Wannier functions that Wannier 90 gives you? Like you say, like you are checking the localization of your
matrix element.
Yeah, matrix elements. So I am still like because I would like in some systems I may binarize to check, but I don't actually know a way of doing it fast.
Yeah. So actually, when you perform the linearization in the output, you should have the spread, and that tells you essentially in angstrom how much the function is localized. And okay, the fact that the Wannier functions are localized is not automatically reflected on the fact that other operators are, but there's a very good correlation. So if the linearization is performed well and the functions are localized, there is a high chance that everything gets localized as much as possible, let's say. So that's not to say that it's automatically localized because it depends, but it should be as localized as possible. So the fastest way, just to answer you, the fastest way I would say is just to check that your Wannier function are, yeah, that's right.
I mean, not myself, but collaborators that they don't, so I mean, science also, like, yes, you have the spread by Wannier and also the sum of the spreads, but sometimes, depending on how the spread is, because they're not working in systems that they know they have to have an obstruction, it looks like everything is localized, but then when you actually plot it, I don't know how, essentially, I don't remember how is that spread computed, but so this collaborator is essentially plots and extrudes them to see the actual Wannier function, which is very painful to do. Okay. So I was just.
So actually, we still didn't specialize on this topological part in EPIq. But I know that there is a large community of people that are working on this kind of on other software, Wannier-based software. Well, actually, Wannier is a very rich ecosystem. Let's say there are many programs working on this. Like, for example, I know Wannier Berry here in San Sebastian, but also.
One of the developers, Wannier 19, is working here.
Yes.
So if we didn't listen carefully to the discussion, but just keep on working on the tutorials, we would be having this plot that is just the plot from before, where indeed I also compute different, so it is the line width for each mode at different temperature. But the difference between solid and dashed line is that the solid one are computed with, let's say, with less Q point than the dash one. So the dash one were computed on a grid that is 24-24. Instead, the dash one, the solid one are the ones computed before with the 4x4 grid. And as you can see, there are a lot of modes that are not at convergence, so there is a big difference between the dash and the solid line. But you can also see that if we are going up to a very high temperatures, the modes just overlap, and so we find that for a really high temperature, for certain mode, it's not really different to use a 24x24 grid, but it's just could use a 4x4 matrix. I don't know if you are already seen this, if you already see these things, but maybe if you are starting to work in the ab initio community, it's interesting to see how convergence study is done. Okay, so let's keep on. Okay, so well, this was all about the harmonic, but what about anharmonic contribution? So why indeed we are here at the SSCHA school. Because indeed this post-processing can use whichever output from an ab initio code. So also, as I was saying before, the matrix, the dynamical matrix computed with SHA. So the only thing we have to do, for example, we can save this as a starting point. We can just rename this file in order to remember that this is computed with harmonic dynamical matrix on a 24 by 24 grid. Then we can change the input file, and that was called linewidth.in. And once again, we have to change just one label that is telling which dynamical matrix we have to use. That would be not anymore din_q, but it would be, let's see if I remember well, .sn .din. Let's see. Let's check. Okay. Good. So if we run again the computation, now it will read and use the dynamical matrices computed with anharmonic correction. There are no files. Okay. I'm not interested in this. Okay. This one. Let's see the output. It is interesting. Okay. So again, it's in parallelize over k point. It's performing the line width, and it said that should be remaining 8 seconds. Maybe it's optimistic. That's okay. No, indeed, it ended up in 9 seconds. So indeed, it's quite 24 is not a huge matrix grid, but indeed 9 seconds are really a few period of time. So let's say it's quite fast, this procedure. Okay, so now we can compare the harmonic and anharmonic line width. In order to do so, we have to change the name of the output file. This one is the anharmonic 24 without question mark. This one will be harmonic 24. Save. Let's name this. Okay.
Anar in the name.
It was a lot of time that I didn't do typos. That's cool. Okay. It's yeah, improve. It was just okay. Let's try again. Okay. So this time the dashed line will be the anharmonic line, and the solid line will be the harmonic line width. You might say that they are not really changing a bit, maybe. You would expect a more satisfying difference. But indeed, if you look carefully at the expression that we are computing, so the line width, we see that indeed this difference comes from not from the frequency of the mode that will be stronger renormalized, but indeed because this frequency cancels out with the definition of the electron-phonon coupling, but indeed it's just the contribution coming from the difference between the harmonic and harmonic eigenvector of the phonon. So it's something that is usually not really cared about. It's just neglected. Indeed, we can see that there is a sensible, significant difference, let's say. And if we instead we look at the, for example, we can look at another of the properties that this calculation has performed. So instead of looking at the gamma Allen, we can look, for example, at the electron-phonon coupling, that is the lambda property. I don't remember the label, so I have to open again. Oh, it was just called lambda. Lambda here and here. So now I will be plotting not anymore the line width, but the lambda function. Q. Let's see what happens. Come out output in. Okay. Okay, as you can see, since lambda indeed depends on the frequency, and the frequency are more sensitive to the harmonic contribution, we can see quite a difference for every temperatures. And just this is the higher mode, but I can zoom in the low energy one. And as you can see, indeed, an harmonic contribution are significant in this system. And what is going on with you? Are you getting the same result? Is it going, yeah, it's too easy, more or less. What is the issue? What? It takes long? That's strange. Have you tried to run the program in parallelized?
No, I cannot get parallelized.
Ah, okay, sorry. That's a pity. Yeah?
I see you using one Q point, which in this case is the end point.
Yes, it's a bit boring.
Yeah, so
Why?
I don't understand if we can use more Q points or how do you check this?
In that case, we just have to scroll down the tutorial and just see that indeed the next exercise, let's say, would include the plot of the line width along a line. That gives just a more appealing graph and also gives more interest, because the power of this software is to perform calculation over a dense mesh, so a great number of k and q points. So indeed, using just a q point is something dull, but you know we are learning, so we just start slowly. So indeed, yes. So what variable would you change in order to compute more q points? Let's see. Now you get in trouble in yourself. Now you make the answer and I continue talking with you. So what will you do?
Yeah, I think the last one.
Yeah.
So it depends. So for example, you can use 4 or 5 Q points, no?
Yes. Yes.
And you need to specify each Q point.
Yeah.
Depending on the symmetry of the unit cell, the space group, or something like that, no?
Yeah, but also you can choose whichever point you like.
Yeah.
So indeed, the only thing you have to remember to change is also the total number of Q points. For example, if I would put 11 Q points here, and then
So for example, if I choose to put like 10 Q points.
Yes.
And I have entered, for example, 20 Q points. So he will read only the first 10.
Yes. Yes. It stops when you reach the number of Q points that you specify at the top. So, for example, if I put 2 points, but I just write 1 Q point, it would be just the gamma point. But as Jon said before, the gamma point is problematic, so we have to get very close to the gamma point, but not quite the gamma point. And
but
now
the Q points here is similar to the one read in case of VASP. When you generate, when you write the K points file, it's similar, no?
I think so. Indeed, I'm not familiar with VASP, but indeed the first 3 numbers of this line are the coordinates of the Q point in the crystal coordinates.
So you need to check the path for the
No, you can choose whichever point you like.
Doesn't matter.
Yeah, and because you can use also grid, you can plot it on, you can compute it on a line, you can do, I don't know, a specific graphic. And the only thing that I didn't explain yet is the last number, this one. As in other ab initio code, this number is the weight of each point. So if you are using, for example, a custom grid that will sample in not an uniform way your mesh, you will need to specify which is the weight of each point. So in such a way, you are describing what is the area that each k point is averaging on. Let's say that. Okay, so well.
Okay, thank you.
How much time do I have?
Minus 5 minutes.
5 minutes, perfect.
Minus 5 minutes.
Ah, so I'm already late.
Yeah.
Perfect. I will end up with this if it runs. And I will leave the last one exercise to be done at home, like the worst teacher. Okay. Let's see. Okay, we should have given to you also, and this will maybe speed up the thing. Okay. No, maybe 5 minutes, because I have to, let's say, run a post-processing that will make my output a bit easier to be plotted. And it's called bandwidth path. Okay. No. Okay. Let's use the right input file. Okay, I'm not describing this just because it's a bit late. But indeed, you have to specify something that you. Okay. This is really intuitive. It's just the same approach as before, so I don't think you would find any problem. Okay. Do you think it's working? Let's see. No. Why is that? Ah, I know. Okay. Ah, that's better. Definitely better. Which I did wrong. This. Oh, something else. I just spotted something else. That's a pity. another try to it. 1, 2, 3, 4, 5. Yeah, I miss at least 2.
Did you actually do part
No, of course not. Thanks. So I have to rerun also that command. Bandwidth 13. Wait, doesn't.
Can the code generate automatically the path like in quantum espresso?
Yes, it will. After.
I don't remember if I put it online because I
Yeah.
had like the same injection that we had. I think I've done it, but I'm not sure. I should check it. But it's definitely something that we will work on, of course. Yeah. Like the band mode in espresso. I'm not sure. I think it's only in the file because it was in the other file. It was a 1 instead of a 11. Not in this one, but in the other.
In the old one, you have spotted a 1.
Yep.
Yeah, thank you.
And also the 001 were like this.
How did this happen? Is beyond my.
So, yeah, both 1.
Okay. Thank you. So we have to try again. One, 2, 3, 4. 1, 2, 3, 4, 5, 6. Whatever. Yeah, 10. So maybe this automatic way to compute this, it would be specifically for me.
Here you put 11. So
Which one I was lacking? This one?
no,
The last one.
The last one? M? No, it wasn't also in the previous file. Ah,
Oh, it's done. It's actually fine because you are missing actually 0.05. But it's okay.
right, it wouldn't be.
No.
This should be right.
Not there, 9. I think.
Yeah, no.
Because we are missing 0.05.
0.05.
The second point.
Then I think that
No, well, maybe we can.
I mean, but the important thing is that you're consistent. Then
Fuck.
we can do
copy
5.
and paste.
Yeah, exactly.
Now you have to 10. 9 to 10.
Seems easy, indeed. Okay, you run the computation for us in a while. What I did wrong now.
These are 9. Not 10.
How is it possible? I copy and paste it. How did it run?
I don't know what they're doing.
Something mysterious is happening. So I have to do this, right? This.
Yeah.
So there was the last point.
Yeah.
Axina now. Help me, Axina.
But you have to redo the line with now. Before.
No, I think
But
they
you
were.
didn't execute the program now.
Maybe we can look at the. Well, maybe it's not. I can re-execute it. Sorry for being late.
No worries.
We are started a bit later. actually. We could go for the coffee break and then.
Yeah, maybe it's
What
a
do
good
you think?
idea. Yeah,
Okay.
why not?
So shall we go for the coffee break and later we see the plots later? What do you think?
Yeah.
Good? Yes. Okay, we let Guillermo work here.
Thank you.